My name is Kainton Genius, and today I'm actually going to show you the intuition behind principal component analysis. And principal component analysis is actually a dimensionality reduction technique where you have data in high dimension and you want to reduce it to lower dimension. Let's take, for instance, data in n dimensions and you want to reduce it to, let's say, r dimensions where r is very much less than n, right? So principal component analysis is actually defined as the eigen decomposition of the covariance matrix. Now I'm explaining this so that you know how to be able to explain the concept. So let me write it down so that you should be able to explain it in this way: eigen decomposition of the covariance matrix. So let's briefly look at how principal component analysis work, how we can actually reduce a data set with m dimensions and reduce it to r dimension. So let's assume this data set is in this way. It has m dimension. When we say m dimension, it means m columns, not actually the number of observations, but the number of features. So we have n by m. I'm trying to reduce it to a data set of n by r. So basically, we are reducing the number of features from m to r, and we are going to perform eigen decomposition of the covariance matrix. All right, so I'll be a little bit technical here, but I'm actually going to I'll also be very clear. When this procedure is performed, we have the result to be a set of eigenvectors and a set of eigenvalues. So the covariance matrix is given by covariance matrix of, let's say, this original matrix. Let's call it X. Let's call this original matrix X. X is this matrix of n by m. So covariance matrix of X is given by X transpose times X, right? So this is the covariance matrix for X. All right. So if we now perform eigen decomposition, eigendecomp of the covariance matrix, what we are going to have is two things. We have a set of eigenvalues and a set of eigenvectors. Right. So when we come to this point, we are basically pretty much done with principal component analysis. But let me go a bit further. But before I continue, let me just review. We are saying that in principal component analysis, we are trying to reduce m dimension to r dimension. And m, the dimension simply means the number of features in your data, more like the number of columns in your data. We are going to perform eigen decomposition of the covariance matrix of the original matrix. The covariance matrix of the original matrix is given by, in this way, where X is the original matrix. And eigen decomposition of this covariance matrix gives us two things: a set of eigenvalues and a set of eigenvectors. Now, this set we have here is of the form m by n. When you m by m as well, because it's a square matrix of eigenvalues. So at this point, we now have this set of eigenvalues, and then we can now relate it to the original matrix, more like we apply it to the original matrix and we have x dot w. So we are multiplying the original matrix with this set of eigenvalues to give us, let's call the new matrix we are having to be T. Well, don't get it confused. What we are now saying is that after working on this matrix X, we come out with a final some matrix that is m by m. And sorry, let me make it a bit very clearer. So you come up with a matrix. When you multiply this matrix n by m, You remember W matrix is n by m, n by m. So you are coming out with a matrix of n by m. So basically, the original data is not lost because you still have the same kind of the same dimension of the original matrix n by m. So the data is actually not lost. But at this point, this new data we have is arranged in this way. Let's say we have W1, W2, all the way to Wm. So the way it is arranged, Wm and Wn. Okay, so the way this data is arranged in such a way that, let me take another color of pen, is in such a way that W1 is greater than W2 is greater than W3, and so on is greater than Wm. So what it then means is that we can actually take WR columns. We can take the greatest column, the columns with greatest loadings of this final matrix. So in that way, we can now take the first few loadings becomes the principal components. So basically, this is how principal components analysis works. So once you have the final data of loadings, you can actually then take the first few, because the intuition here is that the first few loadings will actually be able to capture the variance, will be the component that capture the most variance of the original data set. So if we have R to be 3, R to be 3, we want to reduce to 3 dimension, R is equal to 3. We simply take W1, W2, and W3 and end there. So if we add more components, then we'll be able to capture more information about the data. But most often, the first few components, maybe 3 or 4 components, will be able to give us a clear explanation and represent this data very, very clearly. So I'm going to actually stop here, and I will also like to thank you for viewing. And remember to subscribe. And then the next question, which is question 9, we are now going to discuss what is eigenvalue plots.